Okay, one of the things that would be handy here would be for us to be able to narrow that list down, because like I said, in that last problem we had 24 that we had to check. Okay, it would be nice if we had a smaller list to look at, wouldn't it? Okay. And so there are a couple of tests that we can do on our polynomial, okay, that are called upper and lower bound tests. Okay, and there's one more that I'm going to show you also. But ultimately, again, if we have a polynomial, degree n greater than or equal to 1, positive leading coefficient, keep that in mind. Okay, and suppose that f of x is divided by x minus k using synthetic division. Okay, so if k is greater than 0, okay, greater than or equal to 0, and every number in the last line is non-negative, okay, then we call k an upper bound for the real zeros of f. Okay, now what I'm going to do is go back and take a look at that previous one that we had. And I'm also going to show you another way to set up the synthetic division, because in order to find upper bound, we might want to do a bunch of synthetic divisions. Okay, and we can do them all in a more compact manner than what I showed you earlier. Okay, and so what I'm going to do is I'm going to take the leading coefficients and I'm going to set them up on top of essentially kind of a bar diagram here. And earlier I did -3/2. Okay, and I got my answer remainder 0 here. I'm going to do it again with 2 just to illustrate the process. Okay. Ultimately, you're just going to write less stuff down. We're still doing synthetic division, but we're not writing down all the multiplications. So we're still going to bring down our 2. We're still going to multiply and then add to -1 and get 3 here. Then we're going to multiply and add and get 4 here. Then we're going to multiply and add and get -6 here. Then we're going to multiply and add and get -18 here. Then we're going to multiply and add and get 0 here. Still the last column is our remainder column. Okay, and ultimately we've shown again that this is a 0. Okay. All right, and remember also that 3 was in our list. Okay, and keep in mind that we're trying to find an upper bound. Okay, and that theorem tells us that if all the numbers in the list, okay, are non-negative, then 2 is an upper bound. That means there's no other zeros that are bigger than 2. Okay, but did I get all non-negative in this line? No. That means there could be more that are bigger than 2. So let's try it with 3. If I bring down my 2, multiply and add, I'd get 5. Multiply and add, I'd get 13. Multiply and add, I'd get 25. Multiply and add, I'd get 69. Multiply and add, I'd get something positive here. Okay, bottom line is there any negatives in the line? No. Then that means that 3 would be the upper bound for this particular 0. Because remember a few minutes ago when I zoomed out to -40 to 40 on that and we didn't see anything else? Okay, well, bottom line is that there isn't anything bigger than 3 because 3 is an upper bound. Okay. Now, with the lower bound, okay, it tells us that if k is less than or equal to 0, okay, and the numbers in the last line are alternately non-negative and non-positive, then k is a lower bound for the real zeros of f. Okay, so let's take a look at that. Remember, -3/2 was a 0. Let's do it with -2 and see what the synthetic division looks like. So if we bring down our 2 again, multiply these two, and add to -1, we'd get -5. Multiply those two, we get 10, plus -2, that's 8. Multiply those two, would be -16, plus -14 would be -30. Multiply those two, we get 60, plus 6 would be 54. Multiply those two, we get -108, plus 36, it would be -72. Okay, and you notice that this is going to fit the bill that was in that description. It said that it alternates from non-negative to non-positive. Okay, so non-negative, non-positive, non-negative, non-positive, non-negative, non-positive. True? So we alternate, in other words, between positive and negative. Okay, and so that means that this -2, okay, is going to be our lower bound for this particular polynomial. That means there are no zeros, okay, that are less than -2. So bottom line is, how does that help us? Well, if we go back to our original list that we made, which was right here, and this was our original list, Okay, what would that tell us about these three right here, first of all? Do we need to even check those? No. We know that everything that we have is going to be between -2 and 3. So wouldn't that take our list of 24 and make it much smaller? Okay. So to help ourselves, if we made the original list and then we found the upper and lower bounds, okay, that would narrow our list down quite a bit, wouldn't it? Okay, and so we'd have a lot less to check. Okay, and that's kind of what we want to do, is be able to check a lot less. Now, we also have the advantage of having a graphing calculator. So like I said, that helps us narrow down the list also, because we can see which ones might be and which ones might not. Okay, but in the scheme of things, we should be able to do this without the calculator also. We should be able to narrow down the list, okay, and then start dividing and see which ones work and which ones don't. Okay, questions so far? Right, I'm also going to give you another test that is not in your book right now, but I'm going to give it to you now anyway, because I want you to be able to use it. This is what we call Descartes' rule of signs. Okay. And going back to the original polynomial, we'll use this as our example again. Okay. What we want to do here for Descartes' rule of signs is we want to count how many sign changes there are as we go from term to term. So if we go from this term to this term, did we get a sign change? Okay, this term was positive, this term was negative. Was that a sign change? Yes. How about if I go from this term to this term, sign change? No. This term to this term? No. Okay, this term to this term? No. This term to this term? Yes. Okay, so there's two sign changes here. Okay, so if there are two sign changes, okay, what that means is that there are either 2 or 0 positive roots. Okay, so there's either 2 or 0 positive roots. Okay, and in general, it's going to be the number of sign changes, okay, minus 2 or 4 or 6, etc. Okay, so just for argument's sake, to illustrate, if I had 10 sign changes, then there's either going to be 10, 8, 6, 4, 2, or 0 positive roots. Okay, so this tells us about positive and negative. How many positive, negative? How many positive roots are there? And we'll talk about the negative roots in a minute. Okay, so again, if we just look at f of x and we look at the number of sign changes, that tells us that there's either going to be 2 or there's going to be 0. And in our case, remember the graph, there were 2, weren't they? There was a rational one and an irrational one. Okay? All right? And the next thing I want to look at is opposite of x. If I were to put negative x in there, kind of like my test to figure out if this was an odd or even function, if I were to put a negative x into each of these x's, the odd ones would change sign. The evens ones, of course, would not. And then we'll count the sign changes here again. So starting here with f of negative x, sign change here to here? No. Sign change here to here? Yes. Okay. So that means there's 1 there. Sign change from here to here? Positive to negative again, so there's 2. Then it goes from negative to positive, so that is 3. Okay. Positive to positive? No. So in this case, they're either 3 or 1. Because remember, what am I going to subtract from my count? I'm going to subtract 2, 4, 6 until I get down to 0. Okay, so in this case, that means there's either 3 or 1 negative roots. And in our case, what did we notice? There's not 3, there's actually what? There's 1. Okay. All right, now, knowing that, just thinking of positive, negative, and imaginary, we already know there are 2 positives and there's 1 negative. And since this is degree 5, that means how many of them are imaginary? Remember, degree 5, we should have 5 total. Okay. So that means there's 2 imaginary ones too. And again, we won't be able to see the imaginary ones on the graph because they are not x-intercepts, are they? Okay. Only if we have real roots do we get x-intercepts. Okay. So again, key when looking for positive or negative. Okay. One thing nice about this in terms of narrowing down the list is if there were no sign changes whatsoever, okay, then that would mean there's no positive roots. So wouldn't that take our list that we made and cut it in half right there? Or vice versa, if we found the negative sign changes and there were none of them, okay, then there wouldn't be any negative roots. That would cut our list in half immediately, wouldn't it? Okay, we would take those off. So again, both of these, upper and lower bound and Descartes' rule of signs, are designed for us to be able to, okay, narrow down the list that we make when we make our list of rational roots. Okay. All right. Let's take a look at another one here. If we look at x cubed plus 2x minus 6, okay, they show the graph of this. We can see that there is 1 here. If you look at the possible rational roots here, if we do factors of 6 over factors of 1, okay, if that leading coefficient is 1, okay, then what are our possible rationals all going to be? Okay, aren't they all going to be whole numbers? Okay, remember, we're dividing by 1. There's no other number here besides 1, so therefore they're going to be all whole numbers. But what if I look at the graph and it doesn't go through at a whole number? That means that that 0 right there must be not rational but irrational. So at that point, the only choice here, we could divide this by a bunch of these, but we would never find a 0, would we? Okay, because the 0 is not in this list. It's irrational. So at that point, we'd have no choice but to use the calculator and do the 0 command, and we'd have to take a decimal for it. Fair enough? Okay. Okay. Now, I'll show you one last example here. If we were asked to find the zeros of this is a quartic function. Okay, we would make our list. We'd put factors of 8 on top of factors of 2. Okay, we would make our list. Turns out that there's only 10 in the list at this point. Okay, if we looked at our sign changes, we got 1 there, no, 2 there. So positive, there's either 2 or 0. Okay, if I were to do the opposite of x into these, I'd have this would not change sign. This would change sign. This would not change sign. This would change sign. And again, when we put negative x in there, the odd powers change sign. So if I look at the negative ones, there's 1 going to there, and then 2 going here. So there's either 2 or 0 negative roots. Okay. And if you look at the picture of it, there's 1, 2 negatives, and there's 1, 2 positive. Turns out there's 2 and 2 in this case. Okay, it looks like one of the roots might be 4 here. So I would start dividing by that first. Okay. So if we were to divide by 4, and it looks like negative 1/2 also. Okay. If we divided it by 4, we do get a 0 remainder, which means that x minus 4 is a factor. The leftover polynomial, the remainder polynomial, is here. If we thought negative 1/2 was a 0 also, okay, we could divide the remainder polynomial, okay, by negative 1/2 and show that it is in fact a 0. And then the most powerful part is this leftover part is now quadratic. It's only 3 terms. Okay, so once we have that set up, we have x minus 4, we have x plus 1/2, and then we have x squared, or 2x squared that is, minus 4. Okay. And once we get those two taken care of, and then this is quadratic, okay, then we know how to solve this because this is just a quadratic equation. We can either factor or use the quadratic formula, and we can find all the zeros that come from this now. Okay, and we know that there are numbers that are real because we could see that there are 4 x-intercepts, so the answers to this are real also. So if we factor a 2 out, we can see that the 2 answers here, if we were to factor that down into x plus radical 2 and x minus radical 2, okay, those would be our other 2 factors, which makes radical 2 and negative radical 2 our other 2 real zeros. Okay. All right, so kind of like I illustrated on Friday, okay, when we have something that's higher degree than 2, what we want to try to do is find a factor. Okay, that'll break it down 1 degree. If we have another factor, we could break that down into another degree. And once we have everything that's at least linear and quadratic, okay, then we're home free in terms of finding those zeros because we know how to solve linear and quadratic equations, okay, no matter what they look like. Okay. All right, questions so far? Okay. The